Hello everybody, my name is Moufdi Hadjab from Sila University in Algeria. Today I have to present my work entitled First Principal Prediction of Optoelectronics Properties of Zinc-Tin-Phosphate for Thin Film Solar Cells. So our presentation is synthesized according to these points. First of all, we have to start with the preface and the computational detail. After that, we have to show the results of the structure, electronic and optical properties, and finally conclusion and perspective. So as a preface, and as it was mentioned in literature, the zinc-tin-phosphate can be used as a layer in the fabrication of thin film solar cells. So in the light of the importance of these materials in various optoelectronics applications, our aim in this work was drawn to investigate the structure, electronic and optical properties such as the lattice parameters, the bulk modulus, the structure band gap, and the rest of linear optical parameters. This structure is shown in figure 1, which illustrates the crystal structure of the SMP2 by employing the full potential linearized augmented plane wave FP-LAPW method to solve the Kohn-Sham equation within the framework of density functional theory DFT using the VN2K computational tool. Therefore, for the exchange and correlation, the LDA and the Vosko GGA has been applied to compute the structure and electronic parameters. On the other hand, the linear optical properties have been studied using the semi-local Becke potential, as well as the parameters of our method, as shown in this slide, such as the MTK times Kmax, the K point, Lmax, Gmax, and the values of RMT. So in this slide, the relaxed equilibrium structure parameters such as the calculated lattice constant, the intern parameters U, bulk modulus B, and its first derivative were obtained by fitting the total energy versus volume to Monaghan's equation of a state and with the fourth degree polynomial equation as it's shown in figure number 2 and 3 respectively. So here this table lists the calculated structure parameters according to LD and Vosko GGA for the SMP2, which are in good agreement with theoretical and experimental results obtained under parallelization. So in the slide we have to calculate the band gap or the band structures of our materials along various high symmetry directions in the first Brillouin zone. It's obvious that this material is semiconductor with a direct band gap. By the way, the table number 2 summarizes the calculated band gap within LDA, Vosko GGA, EV-GGA, and modified Becke potential approximations for the SMP2 compared with experimental data and other theoretical works. So the optical properties are considered as an important source of information concerning the electronic bands structures. It's usually deduced from the dielectric function. Here we show the various optical parameters shown in these figures, such as the two parts of dielectric function, the reflectivity, the refractive index, the optical conductivity, and the absorption coefficient within MBG under ordinary and extraordinary polarization. In a summary, the observed value of energy gap is close enough to this obtained experimentally and much better than theoretically reported results. The values of optical dielectric function, refractive index, reflectivity, and absorption coefficient obtained within MBG reveal that the Ziane SMP2 chalcopyrite material have potential to become an attractive material for solar cells applications and advanced optoelectronics devices. As perspective, we will design, simulate, and analyze two structures shown in those figures based on the previous DFT parameters. And finally, thank you so much for your time and attention.